Ladies and gentlemen, I'm Dr. White. It's my pleasure on behalf of the Minecraft team here to introduce you guys. I want to thank them for you guys coming and being patient throughout the day and sitting in on a presentation. Just a little bit of context to provide you guys with. Up until this point today, what we've been seeing are the results of some detailed projects. So this would be teams who've had 2 semesters to work on these projects. As you're going through and kind of watching these guys and you see the amount of work that they put in, one thing to appreciate is that they've been working on this project for about 15 weeks or so. So we're still in the prelim phase, focused on design synthesis at this point, more than constructing physical hardware, which will take place next semester in our detail phase. Without further ado, Jason, I'm going to turn it over to you and Team Minecraft. Thank you.
Good afternoon, everyone. I would like to welcome you to the Moon Ice Northern Excavating Craft, or Project Minecraft as we like to call it, Preliminary Design Review. I'm the project manager, Jason Aronson, and today I'll be taking you through the systems overview. For a little bit of overview of what the whole project is about, we are a lunar ice sampling drill. We're aiming to operate in conditions similar to the lunar poles and obtain ice core samples from those conditions and store them. For the team structure, I'm the project manager. I'm joined today by my assistant project manager, Megan, my thermal team lead, Laura, my structures team lead, Jacob, my electronics team lead, Sammy, and mechanical is broken up into 2 smaller sub-teams. The motor sub-team is led by Virpal, and the drill sub-team is led by Mangum. So without further ado, I'd like to define what we see all of our objectives as. Primary objectives are those which are critical to mission success. Secondary objectives are objectives which are desired, but they are not mission critical. And tertiary objectives are those which are desired, but we are not designing towards them. And for the primary objectives of Project Minecraft, we aim to collect an ice sample representative of what could be found on the lunar polar surface, and then to store that sample within the system itself. Our secondary objectives are to obtain an ice core and then maintain the integrity of that ice core within the system until it can be retrieved. And our tertiary objectives are that we would like to be able to collect multiple samples throughout the project lifetime. And then up here you can see a subsystem definition. Everything that's in gray is the structures subteam. Everything that is in blue is the thermal subteam. And then what might be a little difficult to see, that little yellow box there, that is the electronics contained within our thermal box that will make up the electronics and control subteam. And then everything in red, that's the drill, the motors driving it, and the bar that will raise and lower the drill are the mechanical subteam. For a concept of operations, we plan to start after Minecraft is already on the quote-unquote surface and secured. And during operation, we will drill down into the surface, capture the ice core, then we'll raise it back up and store it, and for some amount of time to prove that we can. From there, one of the big issues that we had to design around is what our environment might be like. So where we started from is looking up what it might be at an actual lunar pole. So we are expecting temperatures in the range of 20 Kelvin if we were to actually go. It would be permanently shadowed, and as such, the surface ice there would be similar to hardened tool steel. At least that's what we can tell so far. We are not expecting any solar radiation because we are in the permanently shadowed craters on the moon. So the only radiation effect that would be actually getting to our system would be galactic cosmic radiation. And this will be the simulated environment that we will be referring to throughout the presentation. However, that's not exactly possible to test on campus. So we came up with some testing parameters to prove that the system will work. This includes a temperature at 225 Kelvin, a hard surface such as hardened tool steel to drill through on top of a block of ice so that we can then capture an ice core from that. The radiation environment is just not testable on campus. We do not have the ability to simulate that right now. And then we would use a vacuum chamber to simulate the lunar atmosphere. With that, we then were able to move into the system level requirements. Two of our main driving requirements here are requirement 1.1 and 1.2, which state that the system shall occupy a volume of less than or equal to 0.125 cubic meters, and that the mass of the system shall be less than 42 kilograms. These requirements were derived because we were imagining that Minecraft would be able to be mounted onto a rover system such as Curiosity, and so we grabbed those requirements off of what might be mounted on a rover system such as that. And then requirement 2.3 is our other driving requirement off of this. The mission time shall be less than or equal to 2 hours, and that's because we want to be able to complete the mission within a feasible amount of time so that testing doesn't take 10 hours. And then for our environmental requirements, the main driving requirements in this case are 3.2, 3.3, 3.4, and 3.5. These requirements state that the system shall function at temperatures greater than or equal to 225 Kelvin or less than or equal to 320 Kelvin. These come from how low we can possibly get the vacuum chamber on campus down to and the maximum operating temperature of our electronics. And then the two pressure requirements, which state that the system shall function at pressures greater than or equal to 1.33 millipascals or less than or equal to 101 kilopascals. That comes from how low we can get the vacuum chamber on campus to and about sea level. For our future validation plans, we plan to measure the dimensions and mass of the system to validate requirements 1.1 and 1.2. Then we plan to test on a surface test sample to validate requirements 2.1, 2.2, and 2.3. That surface test sample would be the hardened tool steel on top of the block of ice that I mentioned earlier. And then we plan to simulate the system to 25 Kelvin to validate requirement 3.1. We would do this using the data that we get from the actual test and then extrapolate that out to prove that it can work at those temperatures. And then we plan to test the system within the vacuum chamber to validate requirements 3.2, 3.3, 3.4, and 3.5. And with that, I'll be handing it off to Maciek to talk about the drill subsystem.
Thank you, Jason. My name is Maciek. I'll be talking about the mechanical subsystem, specifically the drill. So to begin with, we'll be going over the requirements, then talk about the drill decision process, the drill tooth process, and finally the drill force calculations I went into this semester. To begin with our requirements, most of these requirements are about the size of the drill itself. So the drill should have a length greater than or equal to 33 centimeters and an inner diameter greater than or equal to 3 centimeters. These stem from the size of the ice core that we'd like to collect, which is 30 centimeters by 3 centimeters. Therefore, our drill has to be larger than that. The drill shall store the ice core sample for 24 hours. So that is to accomplish our storage requirement. The drill shall translate less than 5 millimeters from its initial central axis. This was a trigonometry equation that we did to figure out how far we can deviate without causing unnecessary forces to the connecting point between the drill and the motor. And finally, the drill shall penetrate a solid with a 6 or greater on the Mohs hardness scale. So to begin with the drill decision process, we were looking at drills that are commonly used on ice coring on Earth. So the most common one of these is the electromechanical drill. This is a hollow drill with teeth at the bottom that break the ice around the ice core and are usually suspended on a cable and drop down several hundred meters into the ground. So this is obviously much larger than what Project Minecraft is attempting to do, and so we were not going to go with an electromechanical drill. The next one we found was the thermal drill. This has a heated annulus instead of the teeth to break the ice, so it melts the ice around the ice core and collects it that way. However, this is again a much larger drill and so will not be used for this project. And finally, we have the chipmunk drill. This is a much smaller version of the electromechanical drill that is also directly connected to the motor. So the interface is very similar to what we envisioned for our project, and therefore we'll be designing ours based off of the design of the chipmunk drill. As you can see here, this is an image of the chipmunk drill in action. It's just connected to a standard handheld power drill, so the amount of force that is needed for this type of drill and the type of motor that is needed for it is not outside the realm of what we're capable of accessing, and so that makes it very simple for us to design something similar to the chipmunk drill. You can see here is our CAD file and the sample of a drill, of an ice coring drill actually in use. Two things I'd like to point out. The teeth on the coring drill, these will be made out of tungsten carbide for ours in order to get through the hard tool steel that we need to get through. And the core dogs that come in here, those will snap off at the bottom to break off the ice from the surface and then hold the ice in place for that 24 hours as we extract it. So next, the drill tooth process. I mentioned that it was going to be made out of tungsten carbide. So the hardest ice that's been found on Earth has a hardness of 6 on the Mohs scale. This is roughly equivalent to a 65C on the Rockwell scale, which is the hardest of hardened tool steel. So in order to break through something this hard, we need something harder than that. What we found was that tungsten carbide has favorable cryogenic properties and is also used in machining frequently, and therefore it serves our purposes of breaking through this hardened tool steel and will work in our environment. You see here are a couple pictures of tungsten carbide bits. The cylindrical one is the type that you typically use in an end mill, and the triangular one is a small one used in a boring bar. We are hoping that we can use a couple boring bar pieces for our drill. We are working to design a way to make that interface possible. However, if that isn't possible, we have a method of creating our own drill bits out of the cylindrical bits, creating our own teeth out of that by grinding them and then brazing them onto the surface to create our own teeth with them. So finally, we have the drill force calculations. So we've been working on calculating the thrust and the torque necessary for the drill to break through material of hardened tool steel. So this has proven quite challenging. The information about it is very limited and generally limited to not hollow bits, just standard drill bits. So there have been a couple things that we've had to modify about the equations in order to fit our own simulation. So we've been working on a Simulink model to collect that data, and we're also working on an experimental method to verify our analytical results. And with that, I'd like to pass it off to Virpal, who will talk about the motors.
Hello everyone, my name is Virpal, and I will be talking about the motor portion for Project Minecraft. So the things I will be talking about is the motor descriptions, their placements, as well as what they will be doing. One of them will be a drill motor, and some of them will be controlling vertical drills. I will also be talking about the ball screws that we'll be using, as well as the lubricant used throughout. So in terms of the motors used for Project Minecraft, we'll be using a total of 3. One will be a drill motor controlling the rotation of the drill. As you can see, it's highlighted here in green at the top. And as Maciek had mentioned, since we had not completed the calculations for what the drill requires from the motors, we had performed trade studies for each sort of condition that the drill may need from the motors. So those conditions are, in case it is, if the motor needs a high, or the drill needs a high torque, low speed, low torque, or both a high torque, high speed. And then as far as the vertical motors, they are highlighted here in red, and those will be stepper motors that we will be using to control the vertical displacement of the drills. So for the drill motor, in terms of the high torque, low speed motor, we selected a stepper on line NEMA 17. For the high speed, low torque motor, we selected the Hacker A208. And for the high torque, high speed motor, we selected the Makita XDT 15 CB motor, or drill. We will just be taking the drill placed within this hand drill. We won't be using the actual hand drill. For the vertical motors, we needed the motors to provide enough power to push the drill down, as well as we needed them to not dislodge the ball screws within them. So that we wanted a high torque, low speed motor. And for that, we picked also the stepper on line NEMA 17 motor. Now, so for the ball screws, you have those vertical motors placed at the bottom here, attached to the lead screw, which is connected to the ball screw here. The motor will be rotating the lead screws, which will cause that ball screw to be moving up and down. That ball screw is attached to a horizontal bar that is holding both the drill motor as well as the drill. And so here you have an image of the interior of the ball screw. You can see these ball placements within them. They're used to lower the friction between the ball screw and the lead screws. So to further reduce friction, we'll be applying a lubricant onto the lead screws. The things we needed from these lubricants was for them to perform at a cryogenic temperature, as well as within a vacuum. That gave us two options to pick from: a wet lubricant, the Payson grease, as well as a dry lubricant, the molybdenum disulfide. We ended up going with the molybdenum disulfide due to it being significantly cheaper than the Payson grease, while still not losing much capability. And also, the molybdenum disulfide has been previously been used in the space environment. And with that, I will be passing on to Sammy to talk about the electrical components.
Hi, hello everyone. My name is Sammy, and I'm going to be going over the electronic subsystem. So just a general outline of what I'm going to be covering. I'm going to be talking about the objectives of the subsystem, then the requirements pertaining to the subsystem. Then I'll be going over an analysis of the power budget of our subsystem, and then the hardware that was selected to meet our requirements. The objectives of the electronic subsystem is to determine that the system is ready prior to operation. And the other objective of our system is to ensure that the Minecraft system has continuity with facility ground. The first of these objectives is to ensure that we don't have undue damage onto the drill, trying to make it do something it wasn't designed for. And the second objective is to ensure that the static charge due to the lunar environment does not cause any damage to our system. Going over our requirements, most of them pertain to the accuracy that our sensors must be able to perform within. This relates to requirements 2.1.2, requirements 6.1, and requirement 6.2. The other two requirements, 6.3, limits the maximum power that can be consumed by our system, and requirement 6.4 establishes a requirement for the control subsystem, which we'll be presenting right after me. Going over the power requirements, the power budget was analyzed for each of the subsystems for our system. This includes the mechanical subsystem, the thermal subsystem, and the electronics and control. As can be seen from the slide, the electronic system did not require much, so the power was mostly consumed by the mechanical and the thermal subsystem. On the top right-hand side, I'd like to note that at max, if we had the drill running at full power and all the heaters on, our system would consume 371.64 watts. That's beyond our requirements, but that is okay. On the bottom left-hand side, I have a list that summarizes the operational power consumption and the storage power consumption. Due to the fact that when the motor is running at full power and the sensors are operating at full, when they're taking measurements, there's going to be more current flowing through those components. There's going to be more heat generated by those. Our heaters do not need as much power going through them at that time. And taking into consideration the heat that's going to be produced by the motors and other components in our subsystem, our system is actually within the power budget of 300 watts. Moving on to the sensors that are going to be used. For the internal temperature sensor, this is a temperature sensor that's going to be used to measure the temperature near other electronics. This includes the microcontroller, the motors, etc. Is a thermistor. The main reason a thermistor was chosen is that a thermistor is really sensitive to change in temperature. One of the main cons of a thermistor is that it has a narrow operating range, but due to its application, this is not going to be a significant factor. Since the thermistor is going to be put on the electronic components such as the microcontroller and motors, they operate within a similar range. They have to stay between 0 degrees Celsius and 50 degrees Celsius, which is the same as the range the thermistor is optimal for. So this con was not really a significant factor. Also, the fast response time will allow us to detect harsh conditions quicker than using any other sensor. Over here, I have an image of where the thermistors are going to be located within our structure. On the right-hand side, this is the thermal box, which contains most of our key electronics. We're going to have 2 thermistors within this box. They're going to be placed on 2 opposite corners. They're shown here circled in blue. The main reason for using 2 sensors is, 1, to offer some redundancy. In the event that one of the sensors fail, we can still continue to operate our mission with no side effects. And the other advantage is to get a more complete image of what the thermal situation within the box is. If there's an uneven temperature distribution within the box, using one sensor would not allow us to detect that. The other place that we're going to be using these thermistors are on the motors that we mentioned. They're similar to the previous application. There's going to be 2 thermistors on each of the motors. The other sensor is on the opposite side of the motor and it's not visible in the image, but it's going to be similar to that. Each motor on our system is going to have 2 thermistors attached to it for the same reasons as before, to offer that redundancy. Moving on, the next sensor that we're going to have on our system is a resistive temperature detector, also known as an RTD. And this is going to be used to determine the temperature of the environment that our system is operating in. One of the main reasons we're going to be using this is to ensure that the system is not being operated at a temperature that it was not designed for, as this might cause undue stresses and not allow us to complete our mission. One of the main advantages of using an RTD is that it has a very wide operating range. This will allow us to measure the temperature from the time it leaves here on Earth, normal day about 290 Kelvin, just 200 degrees Celsius, all the way down to 20 Kelvin that we expect to reach on the moon. All of this can be done using the same sensor, which is pretty advantageous for this application. These RTDs are going to be attached onto the structure. The location chosen for them was on the right-hand side. This is the area where most of the structural members meet, and this will allow us to get a better understanding of best approximation of what the temperature of the entire structure is. The next sensor that we have on our system is a displacement sensor. This sensor is going to be used to determine the depth of the sample that's been collected. The sensor chosen for this application is an IR sensor. One of the main advantages of using an IR sensor is that it has no moving parts. This allows us to not worry about parts getting damaged as much as using a displacement transducer or some other method that has a moving part. One of the main advantages of not having moving parts is that it increases the longevity of our system. Because the system's not going to experience wear due to use, that allows us to use it for more. We also found IR sensors that are relatively cheap and are designed to operate at the exact range that we want to use. So that makes them pretty ideal for our application. Here's an image of where the IR sensor is going to be located. If you recall earlier, Jason shared the animation, which had this bar translating. The IR sensor is going to be located on the bottom of this bar. And as the bar translates closer to the ground, it will measure the decrease in temperature, and we can compute it to be the depth that's been drilled into the ground. The last sensor that we're going to be using on our system is an accelerometer. The accelerometer is going to be used to determine whether our system is level with the lunar surface or whatever surface we're testing on prior to beginning operation. Some of the other thing that's going to be used for is to determine whether our system is actually fixed, whether it's not moving. This is to ensure there's no undue stress or we're not trying to make the drill do something it wasn't designed for. And it'll also be used to measure the loads that are going on within our sensor, just to ensure that if there is something that's going wrong, we can terminate our mission at any time. This accelerometer is going to be located within the thermal box that contains the microprocessor as well. This is just to ensure that it stays within its temperature requirements and is able to perform its mission. With all that said, I'd like to hand it off to Megan Muller to talk about the control subsystem.
All right, as he said, my name is Megan Muller, and I'm here to talk about controls. So first I'm going to take you through basically just a description of the control subsystem, and then I'm going to show you the preliminary flowchart we have for our program that's going to be running and doing all these things with our system. And then I'm also going to talk about the future plans for the controls and electronics subsystem together. So first, we're going to talk about the board. That's going to be our onboard computer. It's going to be the TM4C123GXL. This is a microprocessor board from Texas Instruments. And it has all of the peripherals that we want. Basically, it has a general purpose input-output, analog to digital converter, and a pulse width modulator. These will be useful for driving the motors and taking the inputs from our analog sensors, which are the RTD and the thermistors. And it also has some digital communication, which is the UART and the X2C. Basically, all of these peripherals being present on this board mean that we can adapt to design changes a lot better because we have all of the things we need already. We won't need to buy expansion boards in order to get these peripherals. And it's also a good board for this project. It's a familiar board from the microprocessors class here on campus. So it's a very familiar development. The program flowchart, this is a simplified version, but we have this mission program loop here, and it's basically got three main parts. We're going to read our sensor data, we're going to interpret it, which is basically converting any values that come in as resistances or voltages and interpreting those into actually the temperature or a distance. And then adjust our mission execution. And these two over here are going to be separate threads, probably run by interrupts, that are basically saying, are we still spinning our drill? Do we still need to be doing that? And are we still going to be moving the system up and down? And so that adjust mission execution block looks at the local temperatures, local distances, things like that, to determine, are we overheating anything? Is anything getting close to being too cold? And it can then turn on heaters, turn off heaters, or even turn off our motors and let them cool down for a time if we end up overheating or getting close to overheating. So future plans for this is that we have some things we need to finish prior to completing all of our validation. And that is to complete that flow chart. If I go back, it's just been this that we've put together, is this mission program loop, which is from the time we start moving the bar down and we're spinning our drill to the time when we finish collecting the sample, or finish drilling the sample out rather, I should say. Because collection is part of what has not been put together on the program loop yet, which will be to let those core dogs snap the ice off and lift it up. This is just until we get down to the bottom that I've developed for the program so far. So that needs to be finished and the program needs to be written. We also need to analyze and characterize our sensors. So like I mentioned, some of the sensors are going to be giving us resistances or voltages instead of actual values, and we need to know how to convert from that into the value we want. And especially for the thermistors and the RTDs, these are going to have curves or data points that we need to take ourselves to figure out some constants for those so we can convert. And then the validation itself is going to be just to combine all of these things. But the first part is going to be testing the program so that we don't damage any of our components. We're going to use signal generators or sensor stand-ins like resistors or potentiometers so that we can divot some inputs that mean something has gone wrong and see how it responds. And we want it that, as we said before with requirement 6.4, we want it to respond within 1 second, and we want it to respond in such a way that it will save the system. We won't end up destroying anything so that we can't continue. And so once we're satisfied with the program, then we will start plugging everything in and see if it still works the way we expect it to with the actual components, and we can adjust from there as well. So this is basically just to keep everything divided enough that we don't destroy anything on accident. And with that, I'm going to pass it off to our thermal subsystem with Laura Rudnick.
Thank you, Megan. Hello, my name is Laura Rudnick, and today I'll be going over the thermal subsystem for Project Minecraft. In overview, I'll be going over the objectives and requirements for the thermal subsystem, the thermal unit description, some ANSYS analysis that was conducted, and the future work needed on the thermal subsystem. The objectives of the thermal subsystem are to ensure that the electronics on board Project Minecraft can function in a 25 Kelvin simulated environment, and that the electronics and motors will function in a 250 Kelvin test environment. There are 3 requirements for the thermal subsystem. The first being that the ice sample will not reach a temperature above 70 Kelvin. And the other two, 7.2 and 7.3, these requirements dictate the thermal range for the thermal unit that will be housing our electronics. The thermal unit, as seen on the screen behind me, has dimensions of 84 millimeters by 57 millimeters by 74 millimeters, so it's pretty small. It's large enough to house all of our electronics though, as well as the thermistors to keep tabs on them. It'll be made up of 3 millimeters of aluminum, covered in 10 millimeters of aluminized mylar to help keep it nice and toasty inside. A similar unit makeup will be used to make thermal shielding around the motors to make sure they also stay within their operating range of 263 Kelvin to 323 Kelvin. Patch heaters will be used to ensure that this temperature range is maintained within the thermal unit. Each patch heater used on board Project Minecraft must produce 0.48 watts per centimeter squared, and this number was gathered from our ANSYS analysis. For the simulated lunar environment, 5 patch heaters will be used within the thermal unit, and for our testing environments, we'll only be using one of these patch heaters. The patch heater shown below is the one that will be used for Project Minecraft. It is a 25mm by 50mm patch heater that requires 12 volts and 7 watts. Seen behind me is the ANSYS analysis done for the simulated lunar testing of the thermal unit. This is simulated with an outside temperature of 20 Kelvin, and it gives us an internal temperature of 312 Kelvin, which is right in that thermal range outlined in our requirements. Some future work needed for the thermal subsystem is analysis on the drill motor and if it will need thermal shielding or not. This will be done once the drill motor is chosen. And then analysis on the heat output from the drill motor will also need to be analyzed to see if the heat output by the drill motor will affect that first requirement of keeping the sample below 70 Kelvin. Then an ANSYS model will also need to be done for the stepper motors, thermal shielding, just to ensure that those predicted temperature ranges are accurate. I'll now pass it on to Jake to talk about our structure subsystem.
Thank you, Laura. All right, so I will go over, as an outline, I will go over the requirements that were illustrated for the structure subsystem to fit within. I will then go over the structure specifications as well as the design that I had chosen and modeled, and then I will actually go over the simulation and modeling that was performed to validate this structure system. So the first requirements that I had to obviously take into account were the system level requirements. That was the entire system can be no larger than 42 kilograms, and the entire system must fit enclosed within a 1.125 meter cube, which is a half meter on each side. But particularly to my subsystem could not exceed 10 kilograms, as just it was validated due to the fact by an assumption of aluminum being used as well as the space that it was allowed to inhabit and make space for the other drill components, i.e. there was a volume of the drill that was already calculated, and that volume was then subtracted from the overall volume, leaving me with a margin of error I was allowed to deal with. Second of all, the structure shall not encounter a stress greater than 214 megapascals. This is the yield strength, the ultimate yield strength of aluminum. This was a very conservative force applied to it so that if we encountered any forces that could break aluminum, obviously we're in trouble, and it would allow us to resort to stronger materials in case of that failure. So as far as materials are concerned, we had chosen aluminum 6061 80/20 bars. The rationale for this is that 80/20 in and of itself is actually cheaper than round stock or square tube. And it also has an intense amount of modification applications. As you can see below in this picture here, this is just one of the many. The 80/20 company actually offers about 3,000 fastener types for their modifications. And it's just a very simple bar as well as an adjustable screw setup. You would have a hole in this 80/20 aluminum stock here, place it through and adjust whatever tightness you need to another aluminum stock. It would also make wiring the structure significantly easier due to the channels within it. This here is the entire structure apparatus. Particularly these points of interest are these linear ball screw shafts, which we had applied simulations on. The entire drill apparatus, which is composed of the individual drill coring mechanism, the drill plate, and the motor itself. The drill plate connects the two main pieces. The electrical box, which you've just gone over, and the stabilizing collar, which is assumed to be a static, non-moving, non-load-bearing item. So it was not simulated. As we've seen this animation before, the points of interest that were simulated was this top bar moving down, as well as the reaction loads going in to this lead shaft screw. And then, of course, entering an assumption that the drill hits the surface of the ice and enters a locked state, i.e. the drill is reacting to going into the ground. And all of the moment is being applied back torque into the motor, into the drill plate, into the screws. So those are the assumptions used to do the simulation. There we are. So the testing pass-fail criteria for all this is, one, separated down to these crucial components. The ball screw in and of itself, as well as all the other components, cannot exceed a stress encountered of the 214 megapascals as determined by the requirements. But particularly for our case, we cannot have a deflection greater than 4 millimeters within the lead screw shaft of the ball screws. And the rationale for this is that within a ball screw to function, especially as far as the lead shaft is concerned, it cannot have a 75% deformation greater than its original diameter. The original diameter for our lead shaft ball screw is 6 millimeters. So we applied a 5 Newton meter force for the drill, which is from the big purple Havoc or Hacker motor, high RPM, as well as a force of 130 newtons pressing down on the drill. This was gathered from calculations that were for a back driving torque on the ball screw. So here's the first ANSYS model, and the reason why we did the top bar is in order to get the force reaction in the Y direction that would be applied to the lead screw shaft. We got a reaction in the Y direction of about 3 newtons. All of these stresses will be summarized at the end. And this was the max stress on the lead screw, but we entered and found a deformation that was within 1.5 millimeters, which is well within our pass-fail criteria. Furthermore, we tested the drill plate, and it is of note that this blue does not mean that it is not experiencing force, it is experiencing compression force. I would just like to emphasize that. And then we simulated the face of the drill. Again, as I said here, the moment is being applied to the face with an assumed fixed position at the bottom, i.e. it has encountered force and is unable to move, so what loads it is experiencing. Here's a table of all the stresses encountered. So the greatest stress that any one of these components encounters is actually in the lead screw, which is 51.6 megapascals. As far as the tension stress is considered, as far as the compression stress is considered, we only encounter something around 1.69 megapascals. So as far as the test pass criteria is considered, we have passed all of this criteria. Future work, as far as I'm concerned, I believe I would like to simulate the thermal stresses. There's a high temperature gradient as we encounter from surface of the moon into the shadowed crater, and there's definitely going to be a bit of fluctuation within the structure, but this would also be segmented to the most crucial points of the structure. I will now pass it off to Megan, who will summarize our entire project.
All right, so quickly we want to go through and talk about if we've validated our requirements. And so at this point, everything has been done analytically, and our system level with our volume and our mass, these have been satisfied. The only one that hasn't is the system shall complete the mission in less than or equal to 2 hours. That's simply because this one is, we have a test plan at very least, or we know the forces that are needed for the drill, or the RPM that we're going to be running the drill at. This is an experimentally validated one, unless we can get all of that information put together before we build and we know more about our system. Then for the environmental requirements, all of these have been analytically satisfied. We saw the thermal box earlier with even the extreme outer temperature of 25 Kelvin for the simulation. It still was able to be within our range that we put forth in 3.2 and 3.3. Then for our mechanical requirements, the ones that have not been satisfied here are 2.2.2, which is that the drill shall translate less than or equal to 0.5 centimeters or 5 millimeters, as it was said earlier, from its initial center axis. And this is because the idea of this one is just when it starts drilling, we don't want it to move from where we started drilling. We're going to lose sample that way. And that's another one that is fairly experimental in the way it can be satisfied. It's not going to be something very easy to do analytically. And the other one is that the drill shall store an ice core sample for 24 hours. This one is very much so, and again, it's an experimental one, and you'll find that I think all of the ones that we haven't satisfied yet are ones that are a little bit harder to do analytically. For the electronics and controls, again, the one that hasn't been satisfied is 6.4, and I described for you earlier the plans for developing to and validating this requirement. And then for our thermal subsystem, the simulation for 70 Kelvin, keeping the core sample at that temperature, we have not been able to do that one analytically because we have not chosen a drill motor yet, so we don't know what the heat is going to be from that. We're not sure what the heat loading on our drill and our core sample would be from a motor if we don't know what the motor is. And then our structures requirements have both been satisfied as well. Jake was just up here telling you how he's done the simulations and the way we've designed it. It's at a good place for the structures subsystem right now. And And so before we take questions, we would just like to acknowledge our capstone professors, Professor Mangum and Dr. White, and all the other professors and students and just people who have helped out on our project. And with that, I'm going to invite the rest of the team up here for questions.
Just a quick note to the panelists, we've got about 10 minutes, it looks like.
Hi, I'm Jody Davis. I'm from NASA Goddard. Good job. That was a lot of information. I'm sure you guys had it condensed down into a very short period of time. So I think I was a little confused just in terms of implementing this on a mission. Would this system be a subsystem of a rover system that you would plan to implement like on a rover? Or would it be a standalone drill system? Because I'm looking at that design and I'm a little confused.
Yes, so the rationale for designing it to a rover is that it would basically trim the fat on the project. We are able to keep it in a low weight and low volumetric requirement. If we made it in its entire subsystem, then we enter a realm where we must start looking at securely clamping it to the ground, methods of deployment. By assuming that we have it on a rover, we are able to mitigate some of these problems by saying that the rover in and of itself is able to keep things stable, is able to keep things in a position-oriented, contact with the ground, and allows us to focus on a structure of this method where a lot of the focus comes in keeping this drill and this structure from breaking apart in these intense, thermally extreme environments, as well as focusing on the actual drill apparatus.
Okay.
If that answers your question.
Yeah, it does. It's a little confusing because looking at that, it's a standalone system, and where I'm gonna poke at a little bit. I didn't see anything about documentation, and then how are you guys defining your interfaces? So we usually, when you're dealing with different organizations, kind of working across interfaces, you have to have interface control documents and interface requirements and things like that. And having this system be a subsystem on a rover, that would be something that you'd have to think about. You'd have to adjust your design to be able to accommodate that rover.
So the idea for this was that this is the system we're going to be testing. It's going to be set up like this. The rover was mostly a way to get some good volumetric and mass requirements, and it is certainly true that this would not be able to interface properly with the rover the way we have built it right now. And I think it was mostly part of the development of the idea of the project for the rover. And we keep coming back to, this thing on the moon, that thing on the moon. But realistically, we're not going to the moon, and this thing isn't going to be installed on a rover. But we still like keeping those things in mind because it helps us sort of give direction to what we want this project to be. And if it were to go past us, what changes, what developments would need to be made.
Right. Yeah. You want to make sure you're flexible and agile, and especially when you don't know who your customer is. That's good. So the other thing that I was wondering, okay, so did you guys consider any planetary protection type constraints? You don't want to go contaminating your samples in any way. That's something that we have to consider when we land things on another planet, let alone collecting samples and caching them for analysis or potentially for bringing them back to Earth. So I don't know if you did consider that, and then also considering dynamics requirements. So this thing will have to withstand launch. And I didn't hear anything about, even though it's probably something you might not do here, but vibration testing, acoustic testing, to make sure that you can handle the launch environment.
You answered the first question.
As far as the planetary constraints, making sure we don't contaminate the sample, what we've really looked at there is we're pretty much assuming that whenever the drill goes down and drills through the surface ice and takes our ice core sample, we'll be able to contain it within the drill and keep it from being contaminated on the outside. And as for the launch dynamics part, I think that would be something for structures.
Yeah, for the most part. It just further harkens back to my explanation that we have studied it and we put it in a report and we said, yes, it can possibly withstand this level of energy going into it. But as far as the system is considerably built, right now it's never going to survive as its current state within a rocket, on the moon. And from my perspective, I obviously haven't researched these topics for the most part because I felt that there were more pressing issues within the structure that needed to be simulated to complete it as it is within an Earth environment, that if I should acknowledge within the lunar environment, then yes, it would take more considerable simulations and time. So as a short answer, I just generally did not consider that as a variable.
A couple questions. Some of your temperature requirements seem to not jive with what was in the thermal part. So just maybe go back through and make sure that everything is consistent. Another one I had noticed is your volume requirement. You need dimensions, you need a box that this thing is gonna fit in, right? You just can't say, I mean, you kind of mentioned a 1/2 meter by 1/2 meter, but that should be your requirement, not to fit into a volume, because you could have super tall skinny thing and still meet that, which is not the intent, right? In general, I kept on thinking you need more requirements, because you said something about an accelerometer to make sure it's level, yet you have no level requirements or inclines or anything like that in your tables here. So it's just, it seems like there's a lot of implied requirements, which you may have written somewhere else, but they need to be consistent. Let's see here, what else do I have? A couple more. Of course, they're all on different pages. You said you were going to operate this in a vacuum chamber. Is that yes, no? And it's a vacuum thermal chamber to reduce it to that 20 Kelvin?
Not down to the 20 Kelvin. That was where the 225 Kelvin requirement came from. That's how low we can physically get the vacuum chamber on campus down to.
Okay, I think trying to equate to what was going to be on the lunar surface and divorcing that from what you're actually going to test. I mean, I understand that you're going through the steel or whatever to mimic what it's going to be like, but it got confusing to me of like what temperature you were actually going to do your testing at, which I realize you can't test like the moon. And is your machine shop okay with tungsten carbide? Like, is that something they're used to dealing with? Okay. A nod's fine. That was good. Yeah, and one thing too is you were talking about measuring like the distance traveled and having your controller being able to tell you that, but then comparing that to an actual measurement. But if it's in a vacuum chamber, how are you going to make the actual measurement to compare it against?
I think the plan was to calibrate it outside without drilling, just moving the bar, calibrate everything piece by piece, and then put it in.
Okay. And I think you did mention some heat transfer analysis.
Yeah.
And sorry, I got a lot of questions. I apologize. But one of the other things is you talked about the structure being a certain weight and the overall weight, but then everything else didn't have like an allocation. So it'd be good to see what we call a mass equipment list of what you expect, the maximum possible, and kind of where you think that's going to land, and then to have margin on top of that. Okay, I think I probably said enough. Yeah.
But good job, sorry.
All right, guys, good presentation. I'm going to keep it quick because we're trying to keep it down to about 10 minutes. I have a few questions. I might talk to you after. No, you're completely fine. Starting off with the presentation was really nice. Transitions were smooth. It looked good. It was visually appealing. So that aspect was nice. The only issue I had was that your sub teams were comprised of one person. So call it a subsystem instead of a sub team. It's not a team. It's just you. So if it's you, yourself, and you, that's nice. But I would call it a subsystem. Let's see. The one thing that bothered me, again, test background, test equipment, driving requirements. Was bothersome. So you talked about how your pressure chamber, your requirement was driven by the pressure chamber on campus. The requirement should be driven by the environment you're designing to, right? You're not designing to operate in a pressure chamber, you're designing to operate on the lunar surface. And I get that you won't be able to test that, that's fine. that's something for detail. Explain why you were unable to test in the lunar environment, not why you didn't design to, right? Let's see, I'll skip a couple here. The raising of the teeth, that bothered me a little bit because all of your images showed the cutting teeth being screwed on to your drill. Have you done an analysis on the screws versus the brazing?
Yeah, so when I was talking to one of the machinists at ACFAB, he was talking about how trying to drill a hole into tungsten carbide bit and then screwing it on could lead to stress concentrations and could cause it to fracture. And so it would actually be simpler machine-wise to braze it onto another surface and then screw that into place rather than trying to screw the tungsten carbide directly onto some piece of drill.
It would certainly be simpler, but I'm not convinced that the analysis is there to back up that it would meet the design requirement. So I'd just like to see analysis on it, just to make sure the
So-
brazing might do fine. I just want to make sure that
I think the images that we have of other existing drills where it has been screwed on, it would be similar to that. Basically, we have just the tip of that piece would be tungsten carbide brazed onto like a piece of aluminum or something like that, and then that would be screwed on. So it would be assembled the same way as the pictures we were showing of existing drills. It would just be that the tungsten carbide had to be brazed on so that, you know, was one solid piece of metal that went from aluminum to tungsten carbide. So it's basically the same thing as has been done before, just we have to adjust it a little bit because we need something harder.
Okay, that's fair. I would like to see that reflected, just to make sure, because again, with that brazing process, it's still, as soon as you bring up brazing, I'm thinking that tooth can snap off, right? And then you've got nothing but aluminum, it sounds like. So just something to keep aware of. I'll skip to this one here. For your storage, because the overall goal here is to make sure that you have a sample at the end of this. And you have 24 hours of storage, but I'm curious as to how you plan to test whether your system stored the sample correctly or not. Is it just, hey, we have a sample at the end of it, or are you gonna look at sample integrity prior to, immediately after drilling, and then after 24 hours to make sure that there was no degradation? No, as she was talking about earlier, no sample contamination, etc. What are you planning to do to actually test your storage more than just, hey, we still have a sample after 24 hours?
I believe we would do something similar to what you said, where we would check the integrity of the core before, immediately after we capture it, and then check it again after 24 hours to ensure that core integrity was maintained.
It's pretty much as simple as that. Measure the length and diameter before and after.
Okay, I just want to make sure that you're monitoring if there's any flaking of the sample, make sure that you're monitoring that, perhaps have a drop sheet underneath just to make sure that you're not losing any of the sample, right? Stuff like that, just to keep in mind when you're going into testing. All right, that's all I have, guys. Good job.